Hi, welcome to another video. Hope you all had a good Christmas. I'm just about complete with my battery management design. I mentioned in one of my earlier videos I developed my own float. To show you the reason why I had to develop my own float, this is a regular float. This is measuring the difference between the maximum voltage and the minimum. So it's 7.4 to the -3. So is that the E for exponent? So that's 7 millivolts difference. That's why I developed my own float, and also I didn't want all the other junk after these numbers up here. We're just interested in these numbers here. I'm taking this millivolt difference and multiplying it by 1,000. So you might see a discrepancy. You might notice a difference of 3 or 4 here, and my number may be 1 under. So that's a regular float, and that's why I'm not using it. So just as a few weeks ago, the low cell is white, the higher cell is red, the difference is now in blue, and that's the total battery voltage. I've now got the microcontroller, 3.3 volt microcontroller, running off this 5 volt battery pack. This 5 volt battery pack supplies 5 volts to the PCBs and 5 volts to this regulator, just here. And I must mention, I spent an hour earlier wiring this up. I received this from Farnell just the other week. It's made by ROM. If you don't put a 22 microfarad capacitor on the output, as they state, you'll get 3.9 volts here, not 3.3. So if you're tinkering about with sensitive electronics and you do not follow the exact instructions, you can blow something up. So therefore, I don't recommend this brand of regulator to the novice, or if you're just prototyping. I've never come across a regulator where you absolutely must have the correct filtering before it regulates down. So this regulator, something to watch out for if you're new to electronics. That's the part number. Have a look at the data sheet. Right, so it's running from a USB battery pack. There's the PCBs. You can see I still haven't sorted the configuration of these 6-way connectors. I had to put a twist in this cable. I've now got an LED on each board. That LED is controlled by I2C. So if I turn this light off for a second, I might be able to see the LEDs more clearly. So that's it flicking through each PCB. You don't have to have the LEDs on if you don't want to. And same as before, that's flicking through the cells here. So I've still got the Murata isolated DC to DC converters. 5 volts going in, up to 5.5 out, into a 5 volt regulator, into a precision reference for the ADC. That gives me 4096. That reference is then fed to the microchip ADC, 12-bit ADC. If you saw my early videos, I was only able to get one address from RS Components. However, Mauser, Farnell and DigiKey do most of the others. And if I zoom in, because you're on a mobile phone, you've got the regular part number, and then the A2, A1, A4, A7, A0 and A6. These are actually taken from DigiKey's site. Those bits beginning with A, they're the address. So you can have 8 of these on one bus. So this is how I'm measuring the voltage on each cell. I communicate with the ADC via I2C, and same as a few weeks ago, on every PCB I've got this low power bidirectional I2C isolator. To sort out the communication on every individual PCB, I've now got this low voltage 8-bit I2C port expander, Texas Instruments, 8 addresses available depending on where you connect the address lines. As an example, on this main board, I'm using 4 pins here. 1 pin turns on an LED, 1 pin enables a boost converter, 1 pin disables the 5 volts going to that boost converter. So when it's turned off, you don't still have 5 volts on the line. So pin 4 on this expander runs down, turns the FET on to discharge the cell through a 3.3 ohm resistor. The first PCB hasn't changed design much. I've still got this Nexperia 425 amp FET connected to the ground of this first cell. To get this FET out of the linear ohmic region, you need more than 5 or 6 volts. So I have 12 volts going to it. And that 12 volts is produced from the 3.3 from this first cell. This isolates the output. So you've got the 4 cells. On the uppermost cell, I have another FET, just an 80 amp FET. That turns the charger on and off. The charging is done with respect to ground over here. This controls the charging and this one controls the output. I did some tests. I put this FET on a PCB, connected it to the cell, put 5 volts onto this gate and it turned on. So I had the PCBs designed without a boost controller on this top cell. However, when I used a different FET of the same family, the same part number, it was a different FET, the cell had a slightly higher voltage, 5 volts would not turn it on. So 5 volts, take 3.3, that's 1.7 volts. 1.7 volts would not turn this FET on. The specification is actually between 1 and 2 volts. So I've had to add another boost circuit here. So high power FET there, 80 amp FET there, 2 boost controllers. Some of you may wonder, why can't I charge the batteries here too and use this to control the charging as well? Yeah, why do I need this? Let me show you. If you stick the 0 volts here on this output, put 14 volts in, current flows through the batteries, through the FET, and whether this FET is on or off, this parasitic body diode conducts. So you turn this FET off, this diode is still conducting. Current's got to flow all the way around back to the charger. So this diode doesn't inhibit the charging. It only drops 0.6 of a volt. So that was no good to control the charging. I had to add another FET. I could have put 2 FETs here back to back, but it's easier just put another one up here. So that's why this FET doesn't control the charging. So why did I resort to discharging high cells with a resistor as opposed to using FET in the linear ohmic region? And I did a video on that. If you want to control a FET in the linear ohmic region, this voltage to the gate has to be very precise, and you have to watch out for thermal runaway. To compensate for changes in current as the device heats up, you need an op-amp. And then if you've got an op-amp, you need some precision voltage to it. Then I thought I could use a 16-bit DAC. That would give me voltages out accurate to the millivolt. I could control exactly what current went through this FET. However, a 16-bit DAC is over £5 each. So £5 each times 4 boards, that's over £20, just to be clever. Once the cells have been balanced, you only pass the current through this resistor for seconds or tenths of seconds. So this is a bit of an overkill. It would be nice, but it's an overkill. Also, using the transistor in the linear region, it heats up, so you need loads of copper around it. So that takes up board space, the op-amp takes up board space, a DAC would take up more space, and then as this heats up, it heats up the ADC and the voltage reference, so the voltage you're reading becomes less accurate. So although this would be very fancy and controllable with I2C, I resorted back to the resistor. It's just easier. So I've got a note here, once the cells are balanced, discharge time is measured in milliseconds. So let's see how accurate this is before I go any further. Well, hopefully that the batteries and this display and the meter are in view. Right, so the first cell, I haven't checked these today. I'll get my meter leads right. Right, negative over here, positive here, right, 3.330 and my display 3.329. Oh, 30 just come up. So you can see it's accurate to within a millivolt. That's the first cell. Second cell, I'm not going to swap the leads, so we'll have the negative. So 3.336, and in red there, it's now gone green, 3.335. So again, accurate to a millivolt. Third cell, 3.337, it's fluctuating between 6 and 7. My display, third one down, 3.335. And the meters fluctuating between 6 and 7. So accurate to a millivolt. Oh, it's come up 3.336. Yeah, so accurate to the millivolt still. Last cell, 3.335, and down the bottom 3.334, 3.333, 34 again. So accurate to the millivolt. The total voltage, I'm slipping on a round post, 13.33 on my display, 13.34 on the fluke. So accurate to the millivolt. So for my discharge testing, I've been using this 150 watt kettle, consuming roughly 11-12 amps. If I move this programmer out of the way, I don't need to program anything, so here's a closer look at the top of the batteries. Here's the output FET. I haven't put a bolt in here for the output yet. That's at 425 amp Nexperia FET. This is a discharge FET. I had some new slimline Nexperia. When I come to design the PCBs, I check the availability and price of the Nexperia FETs, and Mouser and Farnell had run out. So this is just a regular 80 amp FET from RS Components. So just in view here is the 8-bit port expander. This is the I2C isolator. This is the Murata DC to DC converter. You can obviously see the LEDs. Just in this back corner here, that's one boost controller to control the 12 volts to this output FET to make sure it's out of the linear region, so it stays nice and cool when it's running this kettle. So this FET transistor here controls the charging. So charging in here, power out there. That's the discharge FET just behind the cable, can't see it. Hopefully you can there, just down there. Discharge FET, charge control FET. This is a boost circuit built on an additional PCB to give us more than a couple of volts to turn this FET on to control the charging. As I say, the source of this FET is up at 3.3 volts. 5 volts from the port expander, which is under here, would not turn this FET on this PCB. However, in a previous test, that same part number FET did turn on. So to demonstrate the function of this, I already have the positive under the positive nut on this highest cell. I connect this cable to the negative of the kettle. This cable's not really thick enough, it does get warm. So that's a negative. I need a bolt in here, but I was too keen to get it all working. So negative, controlled by this transistor here. The kettle's now on. Oh, you see it turning on and off. What I forgot to mention is I changed the program. If the voltage drops to 3.3, it will turn the boost circuit off, isolate the 5 volt supply, so this output FET will turn off. So if I can get both in view, hopefully you'll be able to see when the voltage falls to 3.3, kettle turns off. When the voltage comes back up, it turns back on. So I've set the voltage to 3.3 just for demonstration purposes. I think in reality I'll probably set it to 2.8, something in that region. So that's the output FET. What about the charge FET? Actually, this is another note. So see, while it's discharging, the deviation between all the cells increases rapidly. So this is the deviation between the cells after discharging it for a few seconds. And see the total battery voltage down to 13.1. Let me connect the charger. I've got this power supply charging at just over 3 amps. Negative on the negative terminal of the battery and a positive in this hole here. Right, so this is now charging. We've got deviation of 17 millivolts, not much. But so this will take a while, and I've noticed at 3.37 the voltage starts rising. So between 3.37 and 3.4 these cells are fully charged. And as I mentioned earlier, everything above 3.4 is really only surface charge. I'll let these batteries come up to 3.37 and I'll turn the camera back on. So see you in a minute. Right, these cells are up to 3.37, so if I start this stopwatch, in my observations when these weren't balanced, took hours to get to 3.37. After that, the voltage rapidly rises. I've got a note on a bit of paper here. Yeah, 3.37 took hours for the cells to get to this value. That was charging at 2 or 3 amps. Now I've currently got this set to 3.49 volts, at which point the battery management system will start bringing the highest cell down to the lowest cell. So when none of these cells were sort of balanced or charged up to the same point, I had massive deviations, and it took a handful of minutes, or 2 handful of minutes, 5-10 minutes, to get the high cell down to the lowest cell. But now they've actually all been charged to one level. The deviation is minimal. Let's see what happens when I get to 3.49. Right, so this is approaching the charge cutoff. 3.49. Deviation, look, 21 millivolts, 22. When I had this set to 3.6, this deviation was really large. Right, this is coming up, there we go. Right, this has now reached the charge point, 3.49 volts. When a cell reaches the charge point, the delay is reduced and it starts flicking through the cells every 100 milliseconds. If you see an LED stay on, it's discharging that cell down to the lowest cell, which you can't actually see at the moment. If you have a look at the charger, you see the charge current turning on and off. I don't know if we can get both of these in view. If you see one of these turn blue, that's being discharged down to the lowest cell. So you saw that one and that one flash on, just blue just for a few milliseconds. So as the charger turns back on, you get a larger deviation just for a split second. Now the longer you leave this in this condition, that deviation will reduce. I'll leave it like this for 5 minutes and then come back. Or maybe just 2 or 3 minutes. As you can see, the deviation down to 3, 6, 22 as the charger turns on. So at this point, really, you would want a float voltage. There we are. It's been running for, what's that, 11, 12 minutes now. I've left the charger up full, and this is the state of the battery voltage. So as that charge voltage levels off, the deviation reduces. Large deviation was when the charger turned back on. So I could turn my charger down to a float voltage to maintain this voltage, or if I simply turn the charger off, there we are, charger's now off. So I just saw the charge was off and this was hovering at the 3.49, which is why the sequence had speeded up. But now no cell is at 3.49, nothing will be discharged. But I could simply leave that charger on as if it was connected to a solar panel. These have all come up to this voltage fairly steadily without much deviation. But to reiterate, initially when none of the cells had been balanced, this was all over the place and I had to wait ages for the highest cell to get down to the lowest cell. You know, maybe 5-10 minutes. And that's when I seriously thought I need an active cell balancer so we're not wasting that energy. That energy could go into the battery pack to run this. It's something I'm still contemplating. But so now this is less than 15 minutes. So from 15 minutes you saw the cells come from 3.37 to 3.48, and it would come up to 3.6 within just another few seconds. So I can say 3.37 to 3.4, these cells are charged. Everything else is just on top. I see a lot of people worry about this deviation. I don't know why, because these cells are not matched. They come off a machine. Now you've seen how this battery management reacts when it reaches the full charge voltage. If I plug this kettle back on, watch this voltage here, 99, look, 70. That's these cells are not matched, and you cannot expect the voltage to remain within a few millivolts of each other. This is 70 millivolts, that's discharging. Oh, and the kettle's just turned off because I haven't reduced the voltage back down to 2.8 yet. So that's my attempt at a battery management system, and I think it works really well. And it certainly brought all the cells up to one state of charge. It protects against overcharge and protects against over discharge. I think it's a good system. And it costs a lot less than some of the other systems out there. So hopefully you enjoyed the series. Hopefully you learnt a thing or two. So this is currently a 32-bit microcontroller, and the whole program, including my own float, 27,959 bytes, so 1.3% of this current PIC, and only 169 bytes of RAM. So this will fit into an Arduino. I'll leave the C file on GitHub and put a link in the show more. If you want to buy me a coffee, make a donation for the C file. The link is also in the show more. Hopefully you enjoyed it. Hopefully you learned something. Thanks for watching. Oh, and have a great new year.